Hello everyone and welcome back to Nunley Math. I'm Aaron Nunley. Thank you so much for joining me here today as we discuss the area of trapezoids. Now this is the fourth video in our series of videos on area of two-dimensional figures and the formulas. We've spent a lot of time developing those formulas so that we understand that our geometric formulas are not something that somebody just simply made up. Rather, they are patterns that people recognized and then created formulas to generalize or describe the patterns that they saw. So far, we've done the area of rectangles, the area of parallelograms, and the area of triangles. The development of the area of trapezoids is actually pretty cool. And then in our next video, we're going to talk about the area of circles, which I believe is the coolest of all. So make sure you come back and check that one out. Just in the way of review, we say that area is the amount of space a two-dimensional figure occupies, or the number of squares that fit inside of a two-dimensional figure. So if I have this 7-inch by 3-inch rectangle, I want to know how much space it takes up. I begin to fill it with inch squares. Inch squares. Now we call them inch squares because they are 1 inch by 1 inch squares. They are a square that measures 1 inch in two different directions. So I fill this up and it makes sense that I can fit a row of 7 1-inch squares all the way across. And I can actually do 3 rows of 7 to get a total of 21 squares. If I wanted, I could fill that in, and you could then see it takes 21 squares to fill in that entire rectangle. We use that to develop a pattern. We say, oh, well, the area is just how many fit along the length by how many I can fit along the width, or we abbreviate that into the formula A equals L times W. And we use that to calculate the area of any rectangle. And then we did several examples of that. In our second video, we talked about the fact that we can do something similar with parallelograms, but when I begin to fill this up with squares, we run into two problems. Over here on the left, you can see part of the parallelogram, this little triangle over here, is uncovered, whereas over here we're covering a portion that we really don't need to cover because it exists outside the parallelogram. The good news for us was we can actually take this triangle over here that is uncovered and move it over here to the right. If I were to cut this using a vertical line or a line that matches at a right angle to the base, what we find is this triangle occupies the same space regardless of which side I put it on. So I can have it over here, or I can have it over here. And by moving it over here to this side, I can say, well, this is going to have the same area as an 8-inch by 3-inch rectangle. Area equals base times height. Notice that the measurements that I use are the area of the base, or I should say the length of the base, and I don't measure the original measure that was given to me, that original slanted line. Instead, I want to see how tall it is, the height, and the height is found by making a line perpendicular to the base. Area equals base times height. Or in this case, this was an 8 by 3, and we could see that it takes 24-inch squares, or squares that measure 1 inch by 1 inch. We then expanded that idea into triangles and said, hey, a triangle is just half a parallelogram. So if I want to know the area of the triangle, all I really need to do is find the area of this parallelogram, which has a base of 15 and a height of 6. And from our previous slide, that formula showed us that we're going to take the base times the height, or b times h, and since the triangle is only 1/2, we're going to take half of this parallelogram. So the parallelogram itself is a 15, or has a base of 15 and a height of 6, meaning it would take 90-inch squares to fill this entire thing. Since my triangle is only half of that, I'm going to need 45-inch squares to fill my triangle. And there again, that's the basic idea of what we're doing here is we're trying to figure out ways that we can take shapes that may not have right angles and we can cut those apart and rearrange them in order to fit square units inside. That takes us to our trapezoid today. It looks like this. This is actually a isosceles trapezoid, meaning that one side is going to match the other. It really doesn't matter if I do an isosceles trapezoid or not. The pattern I'm about to show you is going to work either way. Just like the issue we had with triangles and with parallelograms, the problem of trying to stick squares in here is that some of my squares, when I go to fill this up, are going to hang over the side too much, or some may not fit in there at all. You might have little gaps. As long as you have these slanted lines, you're going to end up with that problem. What we really need is something that has right angles, because then we can see how the squares fit very nicely. But in the case of a trapezoid, it's actually pretty easy for us to turn this into a shape whose formula we already know, and that's by taking the exact same trapezoid and drawing it upside down over here on the right. Notice that all I've done is taken this 8 centimeter side and moved it down here, and I've taken this 20 centimeter side and put it up here. Can you see what happens when I do that? Hopefully you realize that this whole thing, these two trapezoids together, are going to form a parallelogram. And I've gone ahead and I've highlighted or outlined that parallelogram for you in yellow. So we can say that a trapezoid is half of a parallelogram, because any two congruent or same size trapezoids, if I place them side by side, one right side up and one upside down, they're always going to form this exact same shape, a parallelogram. And I already have a parallelogram formula. It is 1/2 the base times the height. 1/2 the base times the height. Now, at first glance, you might be thinking, hey, wait a second, that's the same as the triangle formula. And that's true to a certain extent. In a triangle formula, we said a triangle is half a parallelogram. In this case, we're saying a trapezoid is half a parallelogram, but there is a slight difference. I'm going to suggest that you pause the video and see if you can figure out the difference between my trapezoids and my triangles. I'm going to assume that if you wanted to do that, you already have, and I'm going to go ahead and tell you. In the case of our trapezoid, when I come up with my formula, 1/2 equals base times height, or 1/2 times b times h, it's important for me to recognize that the base of my parallelogram is not the same as the base of my trapezoid. The base of my trapezoid was only 10 centimeters. And when we were working with triangles, we would just take that base times the height, and that would give us our solution. But in the case of a trapezoid, this base, this 20 centimeters, is not how long the base of my parallelogram is. My parallelogram has a longer base than the trapezoid did. The trapezoid goes from here to here, that's 20. The parallelogram goes all the way to here. Do you know how much longer this is? Well, hopefully you realize that this 8 centimeters matches this 8 centimeters up top, because these two trapezoids are congruent. I've merely made a copy and flipped it upside down. You see, the 8 comes down to here, the 20 comes up to here, and what I'm left with is a base for my parallelogram that is 28. It's this entire length. So I have to adjust my formula so that I don't get confused and think that this base is just the 20. In fact, I rewrite it as the sum of the bases. In other words, I call this down here 20 the big base, and this 8 up here is the little base. And when you add those together, that gives you the base of your parallelogram. In the case of this particular parallelogram, I had a base that was 20 and a base that was 8 for a total of 28, which means I would need 1/2 times 28 times 14, or 196 centimeter squares. That's little tiny squares that are 1 centimeter on each side to fill the entire thing. Now, in our previous videos, we talked about the fact that this 28 times 14, which is, I believe, 392, this 392 right here would be the area of the entire parallelogram, but we know that our trapezoid is only half of that parallelogram. So we take half of that 392 and we get 196. Does that make sense? Once you know the formula, it's actually not that bad to do. It's just a matter of taking your formula, substituting in the values for the specific trapezoid you're working with, and then simplifying to get the area. I'm going to suggest that you pause the video, you try this one on your own, then restart the video to see if what you're doing matches what I'm doing. I'm going to assume you've already done that, and I'm going to go ahead and do this. In this particular trapezoid, you'll notice that my big base is 13, my small base is 2. 13 plus 2 is 15. My entire trapezoid that would be made from doubling this. Remember, we're going to make a copy of this, flip it upside down, make a trapezoid over here. The entire trapezoid would have an area of 45. I think I said that wrong. The entire parallelogram would have an area of 45. That is the 13 plus 2, the 15, times the 3 is the 45. But remember, my trapezoid is only half that parallelogram, so it's 22.5. Notice since I'm measuring in millimeters, I'm going to fill this with squares that are 1 millimeter on each side. Does that make sense? This last one looks very similar to that. Notice that this is what we call a right trapezoid, meaning that this side over here has a right angle. I'm still going to formula substitute simplify. I'm still going to take the same formula. I'm still going to plug in my values. Notice my big base is 8, my little base is 5, which means my base on my parallelogram is 13. In other words, if I were to draw the entire thing, the base of my parallelogram, or in this case a rectangle, would be 8 plus 5. So this is 13, and the height is 4. 13 by 4 means that this entire rectangle would have an area of 52. I only want half of that for my trapezoid, so it's 26, and this is going to be actually meters squared. You can see where I cut and pasted that, and I accidentally wrote that it was millimeters. I will go back and fix that later. It's just meters squared. That's really all we have for this. The idea is very similar to what we've done before. It's just a matter of trying to get ourselves to grasp the nature of the shape and how we can make squares fit inside of it. As always, I do appreciate you taking the time to join us here today. I hope that's been helpful for you. Make sure that if it was, you give me a big old thumbs up by liking the video. Make sure you ring that bell so that you can see everything else we have coming out of Nunley Math. I do wish you all the very, very best. You all take care of yourselves, all right? Bye-bye.